Okay, good afternoon. I see people are joining us. My name is Kostas Panos. I'm a professor of EECS at UC Berkeley and co-chief scientist for C3D Digital Transformation Institute. And it's my pleasure and honor today to present our seminar for this afternoon. But first, I would like to tell you just a couple of words about C3.ai DTI's mission. This is a relatively new institute. We started a little bit less than a year ago, and the mission is to attract the world's leading scientists to join in a coordinated and innovative effort to advance the digital transformation of business, government, and society. It is a coalition of some very distinguished institutions. Of course, C3.ai is a participant, Microsoft, but University of Illinois at Urbana-Champaign, UC Berkeley, which is my home institution, CMU, which is my alma mater, KTH, Berkeley Lab, up the Hill, MIT, NCSA, Princeton, Stanford, and the University of Chicago. So within that collection of prestigious institutions, we're pursuing many things from C3DTI. And one of the things that we do is the weekly seminars. What you see here is a list of the upcoming events starting from next week. The seminars happening at 1 p.m. as a webinar using Zoom, 1 p.m. Pacific time. And you can see the listing of subjects that we have coming. Many of them reflect the first call for proposals that was focused on COVID-19 related research that was awarded back in June 2020. And many of the presentations relate to the findings of that. But as you can see, the presentations go beyond that point. We have some more general ones coming up as well. So if you have missed presentations in the past, you don't despair. You can find us. They are on YouTube, and you can easily find them and play them back and see what you have missed. So all of them are there, including the one that we'll be recording today. The format of these presentations is quite straightforward. It is meant to be interactive, so start with a 40-minute presentation. And today's speaker has kindly agreed to be interrupted with questions. But after the 40 minutes, we'll also have a dedicated 15-minute Q&A. And you can use the webinar's Q&A feature to ask the questions either during the presentation or during the dedicated Q&A period. You can upvote a question that has already been asked that you liked it, and we will try to answer as many questions as the time will allow. Some of them we'll answer them in real time. Maybe it will be necessary or appropriate to interrupt the speaker to address a question by voice, but we'll try to get to as many questions as possible. So today's colloquium has the title, "Is local information enough to predict an epidemic?" That is certainly a very topical subject. And it is my pleasure to introduce my colleague in the Department of Electrical Engineering and Computer Sciences, Professor Christian Borgs. He joined the department in I believe it's a little bit more than a year ago, in early 2020. And he is also a member of the Berkeley Artificial Intelligence Research, or BEAR Lab. He graduated in physics at the University of Munich and holds a PhD in mathematical physics from the University of Munich and the Max Planck Institute for Physics. In 1997, he joined Microsoft Research, where he co-founded a theory group and served as its manager until 2008, when he co-founded Microsoft Research New England in Cambridge, in Massachusetts. And until, of course, he joined us at UC Berkeley a little bit more than a year ago. Christian is a fellow of both the American Mathematical Society and the American Association for the Advancement of Science. And his current research focuses on responsible AI, from differential privacy to questions of bias in automatic decision-making. And with that, it's my pleasure to pass the microphone to Christian.
Hey, hello, everyone. Good afternoon. If you're at lunchtime in Berkeley, just don't be embarrassed to eat while I'm speaking. If you're having tea on the East Coast, that's fine as well. So I will share my screen.
And I try to stop my sharing here. Okay.
Okay, good. So what we want to look at is we all know that epidemics don't spread sort of in homogeneous in some heat bars of everybody, but they actually spread on a network of social contacts. And we know that this is quite important, right? Imagine you had a network of isolated cliques of small families. You would never get an outbreak past one family. On the other hand, if you have connected networks and you have people like the president of our university who meets a lot of fundraisers, or the president of the United States who meets a lot of people, you get super spreading events. So the network clearly plays a role. And for data scientists, this answers the following question. Assume you have some local information about your network. You are friends with some phone company and they give you the network of people, and you can sort of look at a person and at their friends and the friends of their friends and so on. So you can sample random nodes in your network and you can look at neighborhoods up to some distance. And the question I want to address is, if you have such information, can you actually predict what happens with an outbreak? Is there one? What's the probability of it? How big it is? Okay, so I will model my epidemics with an SIR model, even though the math will be really about this model and even a simplified version of it. But the general ideas should hold much more general. So I will comment on it as I present the model. So you probably have, so we have some network. We start off with everybody being susceptible. And now if a node gets infected, maybe you start with a random node, at some time it will be infected for some random time, TI. 2 days, 5 days, a week, who knows. And while you're infected, you infect all your neighbors, at least those who haven't been yet infected, at some rate, which may be time dependent. Okay, and then at some point, your time of being infectious is over, and then you move to from the infected state to the covered state. So you have this process spreading on this network. And first of all, I want to make 2 remarks. One is that if you know the time of infectiousness, then you have some rate. You have the integrated from 0 up to the time where you're not infectious anymore. That's your total rate of infection. And if you know Poisson random variables, you see that the probability of infecting people is exactly what I wrote down here. And the second remark I want to make is this model can be generalized in many directions. And then it might not even be an SIR anymore, but something which people call SEIR or something like that. Already this model, for example, if this beta is 0 for the first 2 days, then you would call yourself exposed but not infectious. So this model, as I formulated, contains many more general models. You can have some latent variable, infectiousness. Maybe I can be more infectious than other people. And you could also assume that the strengths of the connections model matter. And so your infection spreads more to some of your friends because you see them more than others. And all of that, if you condition on the infectious latent variable and your infection time t, you get a different formula here, but you still get that independently you infect your neighbors once you condition on your own state. Okay, so this is sort of the most general situation we want to think of, even though I will simplify things to be able to do some math. Okay, so typical choices, if you actually talk about an SIR model, is people usually assume that this rate is constant, even though there's really no good reason for it, but they just do. So then you don't have to integrate here, nice. And second, either they choose exponential random variable for these times, then you can think of 2 Poisson clocks clicking. One of them is, okay, to all my neighbors, I have these Poisson clocks, and if they click before my recovery clock clicks, then I infect them. And if my recovery clicks before them, I don't. And this model is called memoryless. It's sort of mathematically really nice. Whether this is more realistic or this one is probably a matter of discussion. I will actually choose this model in this talk, but that's just a choice I'm making here. Okay, so now let's talk a little about the network. Okay, so the most naive approach about a network is that the network doesn't play much of a role, except that you just have a certain number of neighbors. Okay, so an infected node infects each of its neighbors with some probability. It was the expectation of this guy here. And in the two models, I write it down for you here what it is. So with this probability, I infect my neighbors. And by linear expectation, the average number of infected neighbors is just this quantity, which is called R0. And you see what enters here is the average number of neighbors we have in the network. So if you only knew my number of neighbors, that's all you can say, okay? But that's clearly a little naive, okay? So for two reasons it's naive. First of all, if I get infected by somebody, then I can't infect that person back, because that's not I mean, we don't do that, right? Once I get infected and then I eventually get recovered and sort of, so this person will never be infected by me. So you should not have the degree. You should, and degree is number of neighbors just. And D regular, for those of you who don't know that, that's a graph where everybody has degree D. So in this case, you actually don't have that R0 is the average degree times P. It's actually D minus 1 times P. This is sort of the relevant quantity, which decides whether your infection goes off or not. Second, and this effect is super important, higher degree nodes are more likely to be infected. So if you don't look at the average degree of a random person in your network, you really should look at the average degree of an infected node. And that should be larger. Okay, and now it depends a little bit on your network model. So if you have, for example, just this is a model which is used a lot by the physicists, by the epidemiologists, by everybody. Okay, so you give yourself some degree sequence. So every node has a certain number of neighbors. I has DI neighbors. And then you randomly form a graph. And on that graph, you spread your epidemics. Well, it turns out that R0 is actually, so this is your D minus 1 here. And then you actually should not look at the degree distribution, but you should look at the degree bias degree distribution, because higher degree nodes are more likely to be infected. And if you calculate that, you get actually that you will see that the second moment plays a big role, right? So if you have a small average degree, but a huge variance, that is your super spreading event, which make R0 much larger, okay? So this is really the effective R0. It's not if you infect a random node, but you look at how infectious is a random infected node, okay? And in the very first node, it doesn't apply, but starting at the second, so this is really determining the epidemic, okay? But still, this is only distance 2. So for example, if you had small families with radius 2, well, from this, you conclude there's an epidemic, but you only infect your small families. So this is clearly still too naive, okay? So let's go from the other side. Assume we had the information about the whole graph, okay? Maybe it's not a real infection, maybe it's some spread of a rumor on a network and it's Facebook, and they get asked by the Russians, how do we really sort of get the spreading? And they are friendly to the Russians. Well, let me not go there. So they sort of, but if you want to do an advertising campaign on Facebook and you want to really infect everybody, you know the whole graph. So you would like to simulate which node do I want to infect to really get this spreading. So what do? Well, you could do it, you could simulate for every node your whole infection. This will never scale. So what do you instead? You only do one step. So for each node, you draw your recovery time, then you randomly add oriented edges to its neighbors with the infection probability. So this is just one step of the infection. And you do that in parallel for all nodes, okay? Then you get some random oriented graph, because now each node in your network had originally DI neighbors. Some of these will sort of spread one step. You put an arrow there, and otherwise, right? So if you have a node here, oh, I don't like this color. You have your node here. This had sort of originally a certain number of neighbors, and then some of them actually, they happen to do the infection and the others don't. And you do that for every node in your network, a certain number of infections spread from there. And now you look at this random oriented graph you get that way. And so if you do that, you can look at a node I, and you look at the set of nodes you can reach from that node. And now if you think how an infection really would work, well, if we infect I, it will infect all these neighbors. Then I look, if this guy is infected, whom would that guy infect? And if this guy is infected, who would that guy infect? Now, maybe it will actually show something like that. And in reality, one of these two passes happen because one of them is faster. But if you just want to know who is infected, it doesn't matter, right? So this set is really the set of nodes which will be infected if we start an infection at I. So the probability that a random infected node leads to an epidemic is just equal to the probability that for a random node, this set, this outset of a vertex is of order n, because that would mean that if you infected this node, you would infect a positive percentage of your population. Okay. So this construction actually works very general. You can, because you just run the infection for one step. So whatever your model is, so if it's an SIR or an SEIR or whatever, so if you ever want to simulate an epidemic, you should do this. Okay, so this is a well-known technique. It's probably at least 20 years old. And so that if you have the global network, you can really simulate it. And this works for very general models. But for this talk, I will only consider constant infection rates and a deterministic t. Okay, so what does happen then? Well, if t is deterministic, there's no integral anymore. So this is this. And so now what do we get? Well, now I just independently will for each edge, for each node, I independently infect its neighbors. Right, so all of these will now be independently either infected or not. And so if I look at an original edge in your graph, this will either lead to this. So if I infected this guy, it would infect this guy. And if I infected this guy, it would infect this guy. This is probability p squared. Then you could have this, which is 1 minus p times p. So this is there, this is not there. It's the same thing here. And finally, you could just suppress this link, which will be 1 minus p squared. So you see, if you know percolation, this is directed percolation. Okay, so which is a nice model if you want to do some math. Okay, so here's our problem. Okay, so we have a large network and we want to predict the probability size of an epidemic in the model with constant infection times, which is this random digraph. And the question is, can we do that if we only know local information? And the answer is no. I mean, I already had sort of your small families, but imagine here is sort of a mathematical counterexample. So you have a random graph, everybody has d neighbors, and if you make that random, it will very likely be totally connected. So you have everybody is connected to everybody. And if d is large enough, an infection would spread to everybody. Or if the infection rate is large enough, the infection would spread to essentially everybody. But you could also have a graph which had just square root of n copies of these graphs on size square root of n. So you will just have sort of big families of size square root of n. And then an epidemic would never cover more than one family. So, and locally, you will not be able to see the difference. Both of them just locally look like, well, it turns out like a tree with degree d. Okay, so you can't see that locally. So you would have to really ask your phone company for radius which of the number of people in your network, which is sort of, so in general, as a mass theorem, it certainly will not be true. Okay, so it turns out what you really need is you need an expander. Well, let me go back. So I think here I can sort of, before we go now into the more technical thing, let me step back and try to describe the results before I really formulate them mathematically. So when you have standard epidemic models, you have sort of your differential equations, and you have this reservoir of people you can infect, and you move them from susceptible to infected to removed. And your differential equation describes this. And the thing will only stop once your first reservoir is so low that actually the rate of infection is so small that it doesn't grow exponentially anymore. Okay. If you're on a network, the network could have isolated cliques. And even if it doesn't have isolated cliques, it could be locally very connected. And then it could be very sparsely connected. Then it could again be connected. And if this sparsely is sparse enough, this boundary would actually be enough to suppress your infection. So what this expander, and I will define for you what a large set expander is, but what the expansion does is essentially it replaces on the network what the role of homogeneous mixing was in your differential equation. Okay, and once you have that, so if you have homogeneous mixing or just some matrix of mixing where I have sort of people of certain age and certain demographics, and you have 5 groups and you have rates of infection from one to the other, but you still have this essentially infinite reservoirs of people. So these infinite reservoirs get replaced in a network by this notion of large set expanders. And now if you are a data science, if you have this assumption, then you can actually ask your phone company, they give you sort of a random person and their network. Now you try to infect this random person, look how the infection spreads in this neighborhood. If it grows exponentially, you predict there will be that your virus is really bad, it leads to an epidemic. If it dies out, you predict it dies out. And if you get many random nodes, then the probability that it dies out is the probability that it dies out in your little sort of simulation. Okay, so this is sort of the upshot of the talk, and this should hold for very general models. I can't prove it, but believe it's true in general. So one should actually test whether it works, which I haven't done yet. Okay, so I will want to formulate a little bit more mathematically what local means. I will define for you what some of you might know expanders, but I will define it, and actually what a large set expander is. I will have one slide on what people did before, and then I will want to tell you a little bit about the locality of epidemics and something which is called the Bowtie structure, which those of you are young enough to be around when the World Wide Web started. There was a famous paper by Broder et al. In computer science who sort of observed that the World Wide Web has a so-called Bowtie structure. I will tell you what it is. So I think this is a good point to ask clarifying questions before I go into some more details. Kostis, any questions in the chat or Q&A?
No questions so far at the Q&A. Christian,
do you have any questions? Was I clear? Is there something you want to ask? Seems not. Okay, good. So this is a notion which is old in mathematics. It's called the log-weak limit. And it's, I mean, there's some mathematical definition if you know probability theory, which will sort of involve the weak. I will not tell you. But so essentially, here is the definition. So you look at your large network and you probe it randomly by uniform random vertex. And now you look at the neighborhoods up to some radius r. Okay. Now, if I look at the neighborhood around some random node, it will look random, even if your graph is deterministic. So this gives you a random rooted graph of radius r. And now we say this sequence is convergent if the probability distributions for these random rooted graphs converge. Okay, so it's in principle very simple. And local refers to the fact that we look at these local limits, and weak means that I sort of fix R and ask the convergence for each R and don't do something different. So there's different notions of convergence, never mind. Okay, and I want to make one remark. Mathematically, after we have taken the limit of an infinite network, we can then take the limit of the radius going to infinity. In praxis, if your network is large, if you let the radius grow slow enough, this still works. Okay, so then you don't only get balls of radius r, but you get balls of all radius, which means you essentially now in the limit. So you started with a sequence of deterministic graphs, sorry. I just left. Okay, that was not what I wanted. Okay. So you start with the sequence of deterministic graphs, but you actually get in the limit a random rooted graph because you had this random root. And even if your graph was deterministic, if it's not totally homogeneous, you look at it each time from a different point. And so this is called the weak local limit. So let me give you a few examples because it's very abstract. Okay. So assume you have your sort of the physicist called, I mean, this would be a square-centered cubic lattice. Okay, you have your cubic lattice, and in each center you put another little atom. Okay, think of atoms, and sort of this is some crystal lattice with two kinds of atoms. And now you choose a random root. So this random root will be either blue or red. Okay. And in the limit, this guy goes to the infinite lattice. So you get the infinite cubic centers lattice. And with probability half, your root sits here, which means your root has degree 4. And with probability half, the root sits here. So your root has degree 8. Okay, so if you have an infection which starts here, well, it's less likely to even take off than one here. So this will be the notion of the limit. Okay. And just sort of to give you a few other examples. So if you have a D-regular graph, means everybody has degree D. Okay. If you do random D-regular graphs, they actually converge to a tree, which is also have degree D. Okay, so it's sort of, you know, binary trees from sort of computer science. Well, a D-array tree, everybody has D children. And power law graphs converge to a branching process with power law offspring distribution. And preferential attachment graphs converge to some other branching process with some latent type. Okay, so that is this notion of locality. So we think of something being local if it can be determined from this local limit. That will be the mathematically precise definition. Now, what's expansion? Okay, so let's say you have some network, and now we look at a set of people in the network. Okay, you choose your favorite set of people, maybe 2 people in Africa, 2 in the US, 5 in Europe. And now you say this set has expansion alpha if the number of edges out of this set, so between the set S and its complement, if that grows like the size of the set. Well, once the set is more than half the nodes, you have to change this. But if the set is...
Sorry to interrupt. Your slides aren't showing in presentation mode. I think it's...
Oh, I'm so sorry. Am I still sharing?
Yes, but just in regular view. So it's still on slide 12, title 2A, local weak limit.
I see. So I should then PowerPoint slideshow.
I think it is best if you stop sharing and restart it to resynchronize, Christian.
I'm sorry, guys. So, and I should go into the slideshow or into the, let me see. Do you now have 2B large set expansion?
Yes.
Yes.
And you didn't see the slide before?
We don't know what the slide before was. Could you click before for a moment? Yes, we've seen this slide.
You have seen this slide.
Yes, yes.
Good. So what is expansion? Well, expansion means that, so if I didn't have large here, you would say that no matter what your set is, the number of edges out of the set, so leaving the set, should be proportional to the size of the set. Okay. Now, what is large set expansion? You only require this for large sets. Because to some extent, if I have an epidemic and I have 5 isolated nodes in the world, we don't really care about them, right? So normally in CS, people just ask this for every set S. So this will in particular imply that if the set is one node, that it must have at least one edge out. So you can't have, this would normally imply a connected graph, which we don't want to ask. Okay, so we ask for large set expanders if essentially for all epsilon sets of size epsilon times n have expansion. So again, you can think of if you have this graph Gn growing and stuff, then you should sort of allow the sets S to be large. Okay, they have to grow with n at some rate. And only this is important for us. So it's a weaker condition. Okay. Now, people have looked at this in the past. So there's some work on percolation, actually. So not the oriented version we're talking about here, but just sort of remove edges with probability 1 minus p, keep them with probability p. And then people have very limited results. So if you start with a tree, then they know what the critical threshold is. Well, that is sort of, I mean, Sandy and I learned that in kindergarten, and it's sort of, this is super easy to prove. It's not quite as easy to prove in this particular example, but it's really, this is very technical to prove, but it's not very astonishing that you get this, okay? And it turns out that if you have these graphs which locally look like trees, you can actually determine the size of the largest cluster. Well, Sandy and I learned that in high school, okay? And so finally, they have a little bit more interesting. They have bounded degree graphs, and they can show that at least the critical threshold is local, but they don't know the size of the largest cluster. Okay, so that was pretty much what was known. We thought we could just use the results on percolation and generalize them, but actually even for percolation, this is not good for us. Okay, the world is not locally a tree, and we don't have bounded degrees. We want super spreading events. Okay, so we really want that. We want general graphs. We want a bounded average degree, not a bounded degree. And we want oriented percolation. Okay. So, and now I give you more technically the results. Okay. So now what's the mass? We consider bounded average degree. Okay. So that means the average degree is bounded. We have this notion of expansion. So you're sufficiently connected. And local neighborhoods converge as you send your network to infinity. Okay, so the local neighborhoods are not for graphs with even n, they look like sort of little triangles, and for graph with odd n, they look like little squares. You don't want something like that. It has to sort of settle. Okay, so these are the three conditions. And now we consider constant infection times, which means we have this oriented percolation. Okay, that's what we look at. And now the main results will be that the local structure actually determines the infection threshold, the probability of an outbreak, and the size of an outbreak. And furthermore, the graph will have a so-called bow tie structure. I will describe that for you a little bit more, but this is how it looks. Okay, so let me just say it in one word. So far, that's sort of what Broder and Al observed. They observed that for the World Wide Web, there is a set of internet sites where everybody links to everybody. No, not to everybody, but you can get from my page to, so for example, I don't think I point to Shankar, but I'm sure you can within 2 or 3 links get from me to Shankar, and you can get back to me. So this is called the strongly connected core of the web. And then there are nodes which point into that, and the nodes which are pointed to from this core. And the rest is small component. And roughly, I mean, it's not exact, but 25% of the web look like that, 25% is this, 25% is this, and 25% is this. And in particular, if this is 25%, maybe this is 28%, and it might be 30 or whatever, but they're roughly of the same size. And it turns out that an infection digraph looks exactly like that. And it's super important if you want to understand the spread of an infection. So now I give you the mass results. So assume we have this sequence of graphs. We always have that. So what is this? So remember, the limit was just some infinite graph with a root, and it's random. Okay. Now we take this infinite graph, and on it, for each of the edges of each of the links, we keep them with probability p, and with probability 1 minus p, we throw them away. Now your infinite graph might decompose into many small components. If p is tiny, that's likely. If p is large, that's not so likely, okay? And theta of p is the probability that this happens, okay? So this is the probability that after you remove these random edges, in the unoriented setting, we still lie in an infinite component. And then PC is just the threshold to get such an infinite component. Okay, and now our theorem says that the probability that in this oriented graph, a random vertex has an out component which of size linear in n, is asymptotically equal to zeta of p. Okay, so what does that mean? Well, if p is smaller than pc, then zeta of p is 0. And so an infection started with a random vertex dies out with high probability. If p is larger than pc, then this zeta is positive. And then zeta of p is exactly the probability that an epidemic starting at a random node actually takes off. Okay, so even though this thing was defined for unoriented percolation, it gives us the result for this oriented infection. Has to do with some coupling, which if I did a mass seminar, I would give you, but here I won't. Okay, so morally, okay, so now step back from this model. And if you do it in general, the mass will not hold anymore. All these formulas will be wrong. But what morally this means is to determine the probability of an outbreak. You just collect neighborhoods of random vertices, and then you simulate the infection starting from the center of these neighborhoods. Okay? And if the network is an expansion, then this should give you a good estimate of infection probability. So if you do this simulation and your infection takes off, then you predict there will be an epidemic in the real world with that probability. And if the probability is 0, then you say, well, in a large network, everything will die out and a random node will be infected, and you get what you got in Italy in the very beginning, that you get somebody who's infected and dies out. Okay, so and this moral should probably hold just very general. I can't prove it, but I believe it. Okay, so now to give you really this structure of the bow tie, I have to define things for you. Okay, so as before, out I is the set of nodes which can be reached from node I, and int I is a set of nodes which reach I. Okay, so this is a set of nodes such there is a path into I, and this is a set of nodes such that from I you can go out. And now a strongly connected component is one where you have a path back and forth. So this is a set of nodes that from everybody to everybody you can find a path and you can find your path back. Okay, and then you can order them by size. We'll do that. And then we take this largest strongly connected component, here it is, and we add to it the nodes which point into it. That will be SCC minus. So this will be this piece plus this piece. And SCC plus will be this thing plus that. So this is the set of nodes. Okay, so this is sort of my definitions. Are there questions on that? Okay, so we have this strongly connected component where you have passes back and forth. This is passes into this, and this is passes which reach into this piece. And now the second theorem will say that if P is smaller than PC, nothing happens. You only have these small components and small possible outbreaks. But if P is larger than PC, then the theorem says that the largest strongly connected component has positive percentage. Okay, and all other ones are tiny. And second, it tells you that the size of this plus that divided by n is this zeta, and the size of this plus this is the same quantity. Okay, and now this is the first statement, and the second is if you choose a random vertex in your world, okay, if this random vertex happens to be in this green piece, okay, so if I fall in here, what happens? Well, if I fall in here, I must go into here. Everybody's connected to everybody here, so everybody gets infected here. And these pieces can be reached from here, they get infected as well. So if I infect somebody here, I will infect everybody on this path, everybody in here, everybody there. And this theorem says that essentially up to you may need a few vertices here on the way, but really the majority of people you infect will lie here. And on the other hand, if you don't fall into this set, so if you fall in here or here, if you fall in here, you will infect a few people further out on the right, but this will be very few. And if you fall in here, you also will just infect a few. So this tells us what the epidemic says. It says that the probability of an outbreak is the size of this divided by n, which is zeta of p by this. And the size of outbreak is this, which is n times zeta of p. If you had a real epidemic model where sort of it's more complicated, we have correlations and so on, there's no reason to assume that this has the same size as this, but this theorem should still be true. So this structural theorem should be true. And we should have this bow tie structure, and it should still be true that the probability of an outbreak is the relative size of this is called the left bow tie. This is called the tie. So it's the size of the left bow tie plus the tie will determine the probability of a random node leading to an infection. And the size of this, which now in general is different, will be the size. Okay. And the theorem actually also implies the structure, which I sort of will not derive for you, but it's part of the theorem, which actually tells you that really everybody else has just these small components. Okay, so I formalized for you what epidemics being local means. It means that if you have a sequence of bounded average degree expanders with local weak limit, so that this probability distribution of local neighborhoods settles down, then we find that we can determine the infection threshold and the probability of an outbreak and the size of the outbreak just from the limit. Or in practice, you can approximate it by your local samples. And we have this bow tie structure I described to you. Okay, so this will ask sort of, there are many open problems left. So one of them is generalize it to weighted graphs, right? Let's say I have sort of different rates of infection to the friends I see, sort of my wife I see daily, and my students I see twice a week, and the president of the university I see very rarely. So I have different PIJs. This, I think, will just include, you will get sort of nasty notation. Your notation will be really complicated. I have no doubt that any graduate student who any of us would be willing to take could do this. Okay, once they read my 50-page paper together. Also, this is actually, I said it in the big, it was in my slide, but I should say it again. It's together with Yeganeh and Amin. Yeganeh is a PhD student at Stanford, and Amin is a professor at Stanford. And so this makes the math hard. Okay, I believe this is true. Okay, so if you constant t or you have hidden features, I still believe all of this is true. Okay, now this size will be different from that size, but my belief is that all of this hold. I just can't prove it. So this would be really interesting to generalize it so that I don't have just a proof of concept. And then obviously, if I say so this was just a limit statement, right? So now I have to tell you, well, you sample. How big a radius do you have to sample? Is 2 enough? Probably not. But is 10 enough? Probably. But so can we formalize it? Can we formulate a sort of, can I tell you how big your error is depending how large the network is? How many samples do you need? Is sort of 5 enough? Do you need, or do you need sort of, if your network gets large, you need square root of n samples? That would be really bad, right? So the statistical machine learning estimation question, and that I would actually first analyze in this very simple model we had before. And then obviously an interesting thing to do would actually to do application to real world data. But I have sort of done some math and theory papers on epidemics. And so I would need some of you guys in the audience who actually are actual people work on epidemics to work with you, because I don't think I should just do that on my own. And I think that's it.
Thank you so much, Christian. Let me turn on my light so you can see me. Okay, so thank you much, Christian, for a very interesting presentation. I am not a theoretician myself, but I do have a question most on the practical side to get us going. And of course, I want to leave most of the time for other participants. You already addressed the question that would have asked about the statistical estimation, and I understand this is an open problem, but I have a different question. If you turn the problem upside down, and instead of knowing the existence of a bow tie structure, you can make predictions about the epidemic, could you observe the epidemic and identify the bow tie structure in it? Now, could you use the analysis that you have done in order to identify interesting structures in the network based on observations?
So I don't think that one epidemic would be enough, because you would it's just like you would, right? So I tell you, just do right? If you want to do, let's just go to the internet, right? So if you, I mean, even if you want to do trace routes to determine the topology of the internet, you can't just do one trace route, and you can't, probably it's also not enough to do trace routes just from you. What you really need to do to understand it, you need to do trace routes from between many different pairs. That will give you insight on the topology of your internet. Similar way for the World Wide Web. If you just look at the people you can reach from me, right, because your epidemic happened to start with me, well, this will tell me nothing for the people who would point into me. And so in practice, you would need many epidemics. Now that might be not so unrealistic, right? So you might actually observe the effects of marketing campaigns on Facebook, and there you have many of them, and you could probably then infer. So this is a different machine learning question, which is sort of even more complicated. It's an inverse problem. But I think you could probably do it just by similar methods as you use for trace routes to determine internet topologies. You have to pay a lot of attention in these, because it's, for example, known for these trace route measurings. If you do them wrong, you think you're on a power law network, and you're not. So you have to really pay attention that you understand and control the biases you get from these estimations. But in principle, I don't see why not.
Very good. So I would like to open it to, don't have any written questions, but I would like to open it to any spoken questions from the audience. Because I do have a couple of people I want to point to. Let me follow up in the following way. And Stefano Bertozzi, Stefano, I see you still there. What Christian mentioned is, how does it link to real life experience, and how people who actually know how to deal with epidemics can relate to this work? You know, Stefano, do you have any questions or any thoughts to share on that?
Well, I think it's a really interesting question, and that's what I've been thinking about, is how you apply it. Now, I think it would be very interesting to take this offline and think of the specific case of the prisons, because we're working on precisely this model, looking at how much of a difference does it make the physical infrastructure of a prison. Think of each cell as a node, and those cells vary from size 1 to size 750 within the California prison system from a functional perspective. And we've seen very differential rates of spread within nodes and between nodes in different facilities at different phases of the epidemic, with a complete change after October, when recirculation of air was turned on and when the more contagious variants started to be introduced. So I think it would be a very nice setting in which to test this, because it's hard to get such perfectly defined nodes as you have, and we have daily movement matrices. So we know exactly where everyone sleeps every single night for a year. So anyway, it'd be interesting to take that offline. And that would be that was what I was thinking in terms of reality checking it. And then of course, I can think of lots of uses of it in terms of, I was wondering, for example, what you might be able to do in terms of trying to back calculate the probability of spread in a particular node. So for example, one very large node in our communities is the supermarket. And if you infect a checker, what does that do in terms of possibilities? But yet again, the probability of infection at each of that checker encounter is much lower than it is in many other settings. And so anyway, it was making me think about the difference between how much infectiousness varies as well as recirculation of air and other things. Anyway, it'd be interesting to kind of prove this against some defined nodes and defined communities.
I think that's very interesting. You also bring in an aspect which I'm well aware of, but I didn't mention, and sort of which is that in real life, your network is not static, right? And so when we put weights on these edges, we just assume there's some average frequency of interactions. But who knows? I mean, maybe after COVID, we only go to the supermarket on Saturdays. And now actually this is not such a good model anymore, because actually maybe if I go to supermarkets on Saturdays and you go to them on Fridays, then this network gets sort of disrupted, right? So maybe you could actually do something like the New York alternative parking or so. You sort of, or when we had the oil crisis, that on Tuesday and even days you were allowed to drive your cars if your license plate was even, and otherwise you had to do the odd days. That would be an interesting question, right? Could we sort of, by subdividing the population into subgroups and say you're only allowed in the supermarket on odd days? I think that would never work in the US, but maybe one could try it out in some other countries. But anyhow, this temporal aspect is in the theory not covered, but when you actually do sort of, when you actually apply it to actual data, there is no reason not to take into account. As you said, in these prisons, you probably know a lot about the time variance of the networks. And you probably need some domain experts to exactly decide whether the temporal effect is actually important, or whether I can think of it as essentially just a frequency of interactions which averages out and doesn't really matter. But maybe it does matter, right? You have a night shift of the guards and a day shift, and so maybe it does matter.
So Christian, if I want to follow up a little bit on that, along the path of linking it to actual events on the ground, you mentioned when I asked about the inverting the model, you mentioned machine learning, and I buy that. But when it comes to applying the model in the way that you described it, in order to apply the model and do predictions based from local information to see how the global pandemic is going to go, what would you need to know in order to apply this? What parameters do you need to extract from actual data? And could you talk about that estimation?
So actually, that's a very interesting question. I'm doing some follow-up work on that. But you really would need, right? So there were two effects, right? There is sort of this local information. And it's pretty clear that you could just, if you want to just determine whether it initially will take off exponential, that should be enough to just do your local simulations. But then you need to know the global connectedness, right? And how connected we have to be is actually, again, an empirical question, right? Is one flight between the US and China enough? Well, probably not. But what if you have sort of hundreds of flights? Or but what if your network used to be really connected, right? My definition was, if I have 1 million people, 10% of them must connect to China. But maybe you don't need 10%, right? So maybe you actually, if you have, I would actually worry, right? So if my infectiousness is, if my chance of infecting somebody I see is 10%, if you have 1,000 people between the US and China going back and forth, and which would be very few, right? This would be almost perfect quarantine. But that might be enough to actually make your network effectively globally connected. So that is, again, something one would probably want to do some simulations on, first in some artificial networks, and have some idea that sort of, I mean, it's, okay, from a mass point of view, I would think if you have a constant number of connections between large communities, you have some chance of exporting it from one to the other, but it's just some chance. if you have a number which grows, well, eventually it will move over to the other side. It might take a while, but if you have sort of these millions of people and now you have sort of 10,000 connections, well, one of these 10,000 will get infected, not only one of the 10,000, but many of them. And one of these many will spread the virus. So if you were in a virus which nobody yet saw and we had no countermeasures, I actually think that quarantine would be very hard, because my intuition would be that this mass serum is way too pessimistic for the virus, that you having sort of, I mean, 2 connections I would not think is enough, but if you have a lot of connections, I would think
but you're postulating an open loop situation, right? In reality, people take targeted countermeasures. They do contact tracing, they do people on quarantine, so they react to the spreading. How could this be incorporated in your model?
So that is not yet incorporated at all, right? Because so this is really the spread of an infection when you don't see it yet.
Yeah, exactly. Zero countermeasures, but in reality, I mean, people react, right? So it's a closed loop, right, in a way.
Yeah, even though in the beginning it was probably way too late, right? Where by the time we closed the flights into the US, you had already community spread, but you didn't see it yet.
Yeah.
So, so I think this would again be sort of a good model for an early spread. For if you're totally right. If you do enough countermeasures, you actually really have sort of, you destroy this expansion property I have, and we don't have 10% of the world population.
Okay, I want to see if there are any more questions. I see people starting dropping out because of the time. Any quick questions before we close? Okay, seeing none. Christian, we really appreciate your presentation. Tandy said that it was really beautiful, and I agree. You know, really enjoyed it, and thanks so much for participating. And thank you all for being a part of this seminar. And I hope to see you all exactly in a week. Thank you, guys. Okay, bye.